Hello everyone, I'm Isha. I'm Moksha. And I'm Adya. We are students from Christ University and are doing our BSc in Economics, Mathematics and Statistics.
In today's video, we'll be exploring a method to solve second-order differential equations with variable coefficients.
Order differential equation with variable coefficients is a differential equation where the highest derivative is of order 2 and the coefficients of the dependent variable and its derivatives are functions of the independent variable. Let's look at the general form. The general form is as follows. The second differential of y with respect to x plus p into the first differential of y with respect to x plus q is into y is equal to r, where y is the dependent variable, x is the independent variable, p, q, and r are functions of x, where p and q form the variable coefficients and r forms the non-homogeneous term. Now, there are various methods to solve this type of equation, a few of which are listed below. The first is a solution when a part of the complementary function is given. The second is changing the dependent variable. The third is changing the independent variable. Fourth is a method of variation of parameters. Fifth is a Laplace transformation. In this video, we will be looking at changing the independent variable. To understand the method, let us consider z, which is a function of x. Writing down the general form, we have d square y by dx squared plus p into dy by dx plus q into y equals r. Now, in order to substitute the independent variable from x to z, we need to rewrite the derivatives of y in terms of z. So dy by dx becomes dy by dz into dz by dx. Similarly, d square y by dx squared becomes dz by dx the whole square into d square y by dz square plus dy by dz into d square z by dx squared. Now, substituting these terms in the general form, we get dz by dx the whole square into d square y by dz square plus dy by dz into d square z by dx squared plus p into dy by dz into dz by dx plus q into y is equal to r. Now, taking dy by dz common, we get dz by dx the whole square into d square y by dz square plus d square z by dx squared plus p into into dz by dx whole into dy by dz plus q into y is equal to r. In order to make the coefficient of the d square y by dz square term 1, in order to get it again to the general form, we divide the entire equation by dz by dx the whole square. This will give us d square y by dz square plus d square z by dx square plus p into dz by dx whole divided by dz by dx the whole square into dy by dz plus q by dz by dx the whole square into y is equal to r by dz by dx the whole square. Now we have the equation in the general form. In order to simplify the equation, our aim is to choose a function z such that it eliminates the coefficient of the first order derivative. So this entire term here, we want to equate this to 0. Find such a function z that eliminates the first order derivative, we take the coefficient of the first order derivative and equate it to 0, which is p dy by dz plus d square z by dx squared whole divided by dz by dx the whole square is equal to 0. Cross multiplying the denominator, we get p dy by dz plus d square z by dx squared is equal to 0. Rearranging the terms, we get d square z by dx squared divided by dz by dx is equivalent to the negative of p. Now, let's integrate this on both sides in order to solve for dz by dx. Now, since d square z by dx square is the derivative of dz by dx, the first term becomes ln of dz by dx is equivalent to the negative integral of p. Now, taking the exponent on both sides, we get dz by dx is equivalent to e to the power negative p dx. Now, such a function will ensure that the coefficient of the first order derivative, which is dy by dz, is equivalent to 0. Therefore, the equation becomes d square y by dz square plus 0 plus q by dz by dx. The whole square is equivalent to r by dz by dx, the whole square. Now we can solve this equation in terms of any of the methods to solve higher order differential equations that we've learned before. To summarize, when we get a problem that we wish to solve by changing the independent variable, the first step should be to define z as a function of x, then calculate dz by dx as e raised to the power negative p dx, p taken from the question, and then write the equation as d square y by dz square plus q divided by dz by dx, the whole square, is equal to r divided by dz by dx, the whole square, and solve this equation through any of the methods to solve higher order differential equations. Now we will be demonstrating two example problems which are solved using this method.
Hello everyone. Today we will be solving the given second order differential equation with variable coefficients using change in independent variable method. Now we know that the general form of a second order differential equation is d square y by dx square plus p dy by dx plus qy is equal to 0. From the above equation we get p is equal to 2 by x, q is equal to 16 by x to the power of 4 and r is equal to 0 in this case. Now for this method we take dz by dx is equal to e to the power of minus p dx, that is e to the power of minus 2 by x dx. This becomes e to the power of minus 2 log x. Thus we get dz by dx is equal to e to the power of log x to the power minus 2, e and log cancel and becomes x to the power minus 2 or 1 by x square. Now using variable separable method and cross multiplying we get dz is equal to 1 by x square of dx, and integrating both sides we get z is equal to minus 1 by x. We now substitute the equation we have got in the equation we get from the above. So we get this equation by solving as explained earlier, and now we substitute the value of dz by dx and z in this. So we get d square y by dx square plus q over here is 16 by x to the power of 4 into here dz by dx is 1 by x square. So we get into 1 by x square the whole square. So it becomes x to the power of 4 is equal to 0. Now these two cancel and we get the equation d square y by dx square plus 16 is equal to 0. This can be solved using any of the methods to solve second order derivatives learned before. Now from above we have this equation which can be written as d square plus 16 into y is equal to 0. Finding the auxiliary equation we get m square plus 16 is equal to 0, m square is equal to minus 16 and m is equal to root of minus 16 which is plus or minus 4i. Since m is equal to plus or minus 4i, our complementary function is equal to c1 cos of 4z plus c2 sin of 4z. Substituting z is equal to minus 1 by x, we get the new cf is equal to c1 cos of minus 4 by x plus c2 sin of minus 4 by x. Since y is a summation of the complementary function and particular integral, and our particular integral is 0, y is equal to cf is equal to c1 cos of minus 4x plus c2 sin of minus 4 by x. This is our final solution. Today, we are going to solve the given second order differential equation with a variable coefficient using the method of changing the independent variable. First, our aim is to make the coefficient of d square y by dx square 1. So we divide the entire equation by x. Now, we know that the general form of a second order differential equation is d square y by dx square plus p dy by dx plus q y is equal to r. From here we get p is equal to minus 1 by x, q is equal to 4x square and r is equal to x to the power of 4. We know that dou z by dou x is equal to e to the power of minus integral of p dx in the method of changing independent variable. Substituting p we get e into minus integral of minus 1 by x dx. Now minus and minus becomes plus. So we get e to the power of log x and e and log cancel, so we get x. Dou z by dou x is equal to x. We now substitute this value in the equation we have solved and got from above. That is d square y by dx square plus qy dz by dx the whole square. We have made the p term 0 is equal to r by dz by dx the whole square. Now substituting values of q and r from above, we get d square y by dx square plus q, that is 4x square y by x square is equal to x to the power of 4 by x square. Cancelling, we get d square y by dx square plus 4y is equal to x square, or d square y by dx square plus 4y is equal to z. We have got this since dou z by dou x is equal to x, and from here we by cross multiplying we get integral of dou z is equal to integral of x dx. So z is equal to x square by 2, and this becomes 2z. Now we can solve this using any of the previous methods studied about second order differential equations. Finding the auxiliary equation, we can write this as m square plus 4 is equal to 0, as this is d square plus 4 of y is equal to 2z, where capital D stands for d by dx. Now solving this, we get m square is equal to minus 4, or m is equal to root of minus 4, that is plus or minus 2i. Since the auxiliary equation has a complex number, we get our complementary function as c1 cos 2z plus c2 sin 2z. Now finding our particular integral, we can write it as 1 by f of d into 2z. In this method, to find the particular integral for 2z, we write the equation of d, that is d square plus 4 into 2z. Now we can take 2 outside, and from here in the denominator we take out 4 to get one of the digits as 1. So it becomes 1 plus d square by 4 into z. Now 2 and 4 cancel out and become 1 by 2 into 1 plus d square by 4 whole to the power of minus 1 of z. Now using the expansion, we get 1 by 2 into 1 minus d square by 4 into z. This can be extended more, but any bigger derivative will cause z to become 0, so there's no point in expanding it more. Multiplying z inside, we get z minus the first derivative of z becomes 1, and the second derivative becomes 0. Now we get the final answer as z by 2, and since z is equal to x square by 2, this becomes x square by 4. Thus the final solution y is equal to cf plus pi, and y is equal to c1 cos 2z plus c2 sin 2z plus z by 2. Now this can be written in forms of x, and it will become y is equal to c1 cos of z is equal to x square by 2. So this will become x square plus c2 sin of x square plus x square by 4.
In real life, populations of animals, insects, or even human activities often show seasonal variations. For example, insect populations may grow rapidly in summer but decline in winter. To model this mathematically, we do not just use a simple growth equation. Instead, we use a second-order differential equation that captures oscillations in population over time. Let P of t represent the population at time t. One possible model is d square p by dt square plus k square p is equal to 0, where k square is a constant that represents the strength of the seasonal effect. This equation says that the rate of change of growth itself depends on the current population, leading to oscillatory behavior. Solving in terms of time is possible, but sometimes it is easier to re-express this equation in terms of a new variable that better represents the cycle, say the month of the year or an angle of the oscillation. So we introduce a new variable, theta equals kt. This substitution allows us to study the system more directly in terms of cycles. By the chain rule, dp by dt equals k dp by d theta and d square p by dt square equals k square d square p by d theta square. Substituting into the original equation, k square d square p by d theta square plus k square p equals 0. Dividing through by k square, t square p by d theta square plus p equals 0. This is a simpler form. Its solution is p of theta equals c1 cos theta plus c2 sin theta. Substituting back theta is equal to kt, we get p of t is equal to c1 cos kt plus c2 sin kt. This solution means that the population fluctuates in a wave-like periodic pattern over time. The constants c1 and c2 depend on initial conditions such as the population size at t is equal to 0. The constant k squared determines the period of oscillation. For example, whether the cycle repeats every 12 months, every season, or at some other interval. Thus, by using a second-order differential equation and the change of independent variable, we're able to model and predict real-life seasonal population cycles in a mathematically precise way. Thank you.